the different positioning techniques that we have today in the market to get a position depending on the target you want. Let's imagine that you have this architecture, right? You have a car. This car will have an antenna, a GNSS antenna, able to receive the signals from the different constellations, GNSS constellations. Then we have a GNSS receiver, which is mainly hardware receiver, even though we can do it software as well, but hardware receiver, GNSS, that is giving this is the measurement engine, as I told you, and we are giving these raw measurements to, and the navigation message, you will see later as well, to the positioning engine, and the positioning engine compute a position. This is a typical architecture, easy architecture for a positioning system. When we are computing the most basic solution that we can have today in the market, that you have in your cell phones or everywhere each time we buy a GPS, is what we call the SPP, which is the standard positioning point solution. It's the most simple solution that we can have today in the market. What is doing this SPP is only using information coming from the constellation, GPS only or Galileo only. It means what we call GNSS standalone solution. In the GPS constellation is giving some information, and you have a positioning, which is very simple solution, but you don't need of external sources, external data to improve your solution. Just you are standalone. But then we have another positioning techniques that are a little bit more pushing, more demanding, that are the ones that are based on the provision on additional information to my receiver. Okay? I'm not longer in a standalone solution. I have some sources that are providing me with some corrections, with some information via different channels, for example, a geostationary or a terrestrial link or internet, VHF, 5G, whatever channel I have, okay? In order to improve my positioning, I want to improve my positioning, then I have the SBAS techniques, GBAS techniques, RIME techniques, we have PPP techniques, RTK techniques, differential GNSS techniques. Different kind of techniques to estimate. For example, if we decompose these techniques and what we call absolute positioning techniques, the one that give me a position, an absolute position, longitude, latitude, altitude, or X, Y, Z, okay? Then we have the SPP solution, which is a standard positioning solution, the SBAS solution, a PPP solution, and PPP-RTK. A tractor, for example, a receiver is able to estimate the absolute position. And we have also for example, the SPP is this one I told you before. If we go to a SBAS solution, we need to add a geostationary satellite providing me with the augmented information in order to have a better solution. Or we have PPP. It's a kind of cloud via an internet link giving me some correction information to my positioning engine in order to have a precise position. This is the PPP. We can have also, in the PPP part, you will see in the Galileo that Galileo is able to provide also PPP corrections through the Galileo satellites, through the service, the high accuracy service corrections. Then we will see that in the future we'll have also precise positioning only using Galileo satellites as a standard positioning point as well, because the Galileo satellites are providing with this information as well. And also, not only for Galileo satellites, but also for GPS satellites. We have the relative positioning techniques that are the ones that need to have what we call a base station not far away. For example, here we have a tractor and you have a base station with a distance. This distance is called a baseline. And thanks to this base station, we will have some information coming from this base station in order to improve my positioning. But the thing is that they are called relative positioning because with these techniques, we will have only the relative positioning to the base station unless we have also the information about the real positioning of the base station. In this way, we can estimate the absolute positioning as well. Then this is relative positioning techniques because they are based on the base station solution, but we can estimate absolute positioning as well because if we know, we have the knowledge of the base position precisely. For example, in the relative techniques, we have the system DGPS. Maybe you heard about DGPS or GBAS or RTK, for example. For example, DGPS, every country in the world, we have some reference base stations along the coasts. These stations are providing with some information to the vessels, to the boats, in order to improve their positioning. And you have all the countries. For example, in Spain, we have something like 18 stations around the coasts. Or in GBAS, it's more or less like SBAS. in the sense that it's for aviation, only for aviation, but it's a local service. It means that we have some base stations around the airport providing information to the airplane in order to improve the positioning and provide also integrity, continuity, and availability. Then the difference between GBAS and SBAS is that GBAS is only for airports, only for a local environment, based on differential GNSS techniques through the corrections provided from the base stations deployed in the airport, right? Then this is a relative positioning technique as well. Or we have also we can also decompose the techniques about the target. There are some techniques that are targeting precision. Say, okay, I want to have precision. What does it mean precision? It means centimeter level, decimeter level precision. In this particular case, we have to put the PPP techniques or RTK techniques, okay? Versus SBAS or GBAS, they are meter level. Then, depending on the precision I want, I will use one technique or other techniques. But there are other techniques that don't care so much about the precision, but more about reliability. This is a very important concept that you will learn through the SBAS and integrity concept. That there are some applications, for example, aviation, they don't care about to have centimeter level precision. They don't care centimeter level precision because I don't want to position an airplane in centimeter level. With a meter, some meters, it's okay. But you don't have to get it wrong. You have to be reliable. It means that if your error exceeds a threshold, you need to tell me. You need to tell me, right? Then the idea of this reliability or applications that are more for safety critical applications like aviation, maritime, rail, the idea of these applications is to give confidence in the solution. I want to have high confidence. What does it mean, confidence? It means that if you give me 95% is 4 meters, this confidence for me is not enough. If you give me, you will be 4 meters precise at 95%. It means that 5% of the time, I will be above this. It's not enough for me because I will crash. It's an airplane. 5% of the time, it's a lot of time. Then, giving reliability to my system means to have more confidence. It means to go to, for example, 9 to 9.99999%. This is give confidence, to give a error with a very, very high percentile. Yeah. If the position error exceeds certain limits, it's with a very low probability, but if it exceeds, I will let you know as well. This is a reliable system. Yes? Integrity system, like EGNOS for safety critical applications. There are some applications, they don't care about reliability, integrity, but they care about precision. For example, a farmer that is just in the tractor, say, okay, I want a precision of centimeter level. If you get wrong, 5% of the time, it's like a few meters, well, I will not crash, I will not die. It's not a problem. Then I don't want reliability. But aviation or safety critical applications, they don't care about precision, centimeter level precision, but they care about integrity, confidence, reliability. Other applications, for example, the applications like road or railway, that they are usually going through very harsh environments where the GPS or satellite constellations, they are masked and we cannot access to the signals. It's not enough to have only a GNSS solution, because sometimes we don't have any solution. Then some other techniques, they demand availability, continuity in the solution. Say, okay, for example, let's imagine you are in a car and you are in the city. You go in a tunnel. If you go into a tunnel, you don't receive anymore a GPS signal, right? Then you don't know where you are. Maybe you have already suffered this when you are in a car, you are in a tunnel, and the GPS doesn't know anything about the position, right? Then for this kind of applications, we need what we call a hybridization or sensor fusion. It means to use other sensors to help the positioning. For example, this particular case, we have a GNSS solution, semi-available positioning, but then we will add here sensors like IMUs, which is inertial measurement units, or wheel odometers, or any other sensor I can use, cameras, lidars, whatever, in order to have a compound solution of positioning and have an available solution all the time. On the top of this solution, you can add a lot of things. You can add EGNOS, PPP corrections, you have precise positioning, whatever you want. Then at the end, we can have everything together, right? If you want. For example, this is very important for autonomous vehicles. An autonomous vehicle is going to cities. In the cities, we need a sensor fusion. solutions, okay? Or the rail is going through urban canyons, it's going through tunnels, we need also sensor fusion solutions, yes? Then terrestrial applications, road applications, GNSS alone is not enough. For airplanes, aviation, maritime, farmers, or even autonomous cars, open sky environments, trains or rail, open sky environments, yes. Yes, but not in the cities.